All right, so 2L was the integral from 0 to root 3 of x to the 5th times the square root of x squared plus 1 dx. And so we did the same thing. We did u is equal to x squared plus 1, and du was 2x dx, and put in a 2 and put in a 1/2. And we have 1/2 the integral from 0 to root 3 of x to the 4th root x squared plus 1 and 2x dx. So we can see that x squared is u minus 1. So x to the 4th should be equal to u minus 1 squared. So we end up with 1/2 of the integral. And if u is x squared plus 1, 0 squared plus 1 is 1, and root 3 squared plus 1 should be 4. And we should have u minus 1 squared times root u du. Everybody good with that so far? All right, 1 second. All right, so we distribute the u minus 1 squared to become u squared minus 2u plus 1. And then we put the u to the 1/2 through it, so u squared becomes u to the 5/2 minus the 2u ought to become minus 2u to the 3/2, and then the plus 1 ought to become plus 1u to the 1/2 du. And we'll distribute the 1/2 through as we do the integral. So this becomes u to the 7/2 divided by 7/2, or 2/7 u to the 7/2 times a half would be 1/7 u to the 7/2, and then this one will become minus 2/5 u to the 5/2, and the last one will become plus 1/3 u to the 3/2. Everybody good there? Any questions or issues so far with the top part of it? It's always the evaluation that's tougher, I think, right? So square root of 4 is 2, and 2 to the 7th, what did we say that was? 128. So we got 128 over 7. Kiana, no, I distributed the 1/2 through, I think, so it should be that becomes minus 4/5 u to the 5/2, but then half of that should be 2/5 u to the 5/2. All right, so what did I say we had? 128/7, is that right? And then the minus 2/5 u to the 5/2. That should be minus 64/5. And then the plus 1/3 u to the 3/2 ought to be plus 8/3. Minus, and then let's see, I don't remember what our coefficients were, but they're all 1/7 minus 2/5 plus 1/3. And if we combine that all together, we're going to get 127/7. Minus 64 plus 2 ought to be minus 62/5 and plus 7/3. And you can leave it like that if you want, but I think if you want to simplify it, it sounded like, right? So you got to multiply the 127 by 15. What does that become? Let's see, that should be that 1905 minus 21 times the 62 is 1302, and then 7 times 35, what does that come out to be? That'd be 245. And And then, let's see, the denominator would be 105. Everybody good with that? And let's see, that's what, 603, and then add 245 to that, that'd be 848. I don't know if that simplifies or not, but doesn't divide by 7, doesn't divide by 5. What is 16 and 20? Yeah, it doesn't divide by 3. So there's the final answer. You good with that, Nick? And everybody?
Yes, thank you.
No problem. All right. So everybody good? Any other questions on any of the problems from last night before we get started with the new stuff? No. All right, I think we left off on one of the ones that was an indefinite integral right here. Integral from 0 to 1 of the inverse tangent of x dx. Does that look right? I think we've done e to the 2x sine 3x already. All right, so I don't think we've ever actually anti-differentiated an inverse trig function before. So we're going to have to use a new method here. We're going to use our integration by parts method. And so hopefully you remember we got to split this up into a u and a dv. And since we don't know how to integrate inverse tangent already, the only other option for our dv value is just the dx that's sitting there. So if dv is dx, then v ought to be what? Just x, good. And then u is going to be inverse tangent of x, so du ought to be 1 over 1 plus x squared dx, since we know how to differentiate that. Everybody good so far? Okay, so our value here then should be x inverse tangent x, u times v, minus the integral, and we're gonna remember, since this is a definite integral, we're gonna evaluate that part from 0 to 1, and then we're gonna have a new integral, which is the integral of v du, or x over 1 plus x squared dx, evaluated from 0 to 1. Everybody good with that? Any questions or issues there? Okay, so the x inverse tangent, well, we'll worry about evaluating that. We'll leave that as x inverse tangent x from 0 to 1. Just for a minute here. Minus this integral. How are we going to do that integral? Yes, Adrian, that's going to be a u sub. Let me see what your question is here, Nick. How can I make v equal to x when it's not in the original integral? I can, because remember, yeah, the integral we're looking for is the integral of u dv. So it's okay. I don't need to have v in there. I just need to have u and dv in there. Does that make sense, Nick? Yeah. All right. So yeah, Adrian, that's going to be a u sub. So u is going to equal 1 plus x squared. So du is going to be 2x dx, which means we need to put a 2 in here and a 1/2 in here. So this now becomes 1/2 the integral, and that integral is going to change limits. So 1/2 the integral of du over u, and the 0 becomes a 1, and the 1 becomes a 2. Everybody good with that? Okay, so might as well evaluate this now. So x inverse tangent x, that becomes 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0, which is just 0 times 0. And then minus 1/2 of the natural log of the absolute value of u. And that has got to be evaluated from 1 to 2. Good? Everybody good there? So what's the inverse tangent of 1? That ought to be pi over 4 minus 1/2 natural log of 2 minus 1/2 natural log of 1. Natural log of 1 is 0, so we end up with pi over 4 minus 1/2 the natural log of 2. Good or no? And we might want to note that had we gone through and not been evaluating this, what would our integral of inverse tangent of x ended up being? It would have ended up being x inverse tangent x minus 1/2 the natural log of the absolute value of this u value, which was x squared plus 1. Oh, yeah, you're right. Sorry, you're right. That should have been a plus 1/2 natural log of 1, right? But still 0. So if I distribute that 1/2 through. So just a quick side note here. Our integral of inverse tangent of x dx should end up being x inverse tangent x minus 1/2 natural log of absolute value x squared plus 1, but that x squared plus 1 is always positive, so it doesn't need to be in the absolute value, and then plus a c. So if you want to memorize that one, it shows up every once in a while. Might be a good one to just know, but you can also do it pretty easily using integration by parts. So any questions or issues on that? All right. Let's take a look at a couple more that are similar to what we've dealt with in the past. What do you guys think here about the integral of x cubed e to the x? What should we do with that? It's going to be integration by parts, so what should our u be and what should our dv be? So yeah, our u value should be our x cubed, and our dv should be our e to the x dx. So du is 3x squared dx, and v should just be e to the x. Everybody good with that? And then we end up with u times v, so x cubed e to the x minus the integral of 3x squared e to the x dx. Everybody good with that? And then what? We're going to have to do the same thing again, right? Except this time we're going to have a different u value. Our u value is going to be 3x squared, so that du is 6x dx, and our dv is going to be e to the x dx, so that v is just e to the x. Everybody good with that? So we end up with x cubed e to the x minus, and then our u times v, which is 3x squared e to the x, minus the integral of v du, which is our 6x e to the x dx. And once again, what are we going to have to do? We're going to have to integrate by parts because 6x e to the x is still a problem. So now we'll have u is equal to 6x e to the x. I'm sorry, just that's why I wrote e to the x. With du equal to 6 dx, and dv should still be e to the x dx, while v is just e to the x. Everybody following that so far? Okay, so this becomes x cubed e to the x minus the 3x squared e to the x. This becomes a plus when I distribute that through. So we're going to have plus u times v, which is 6x e to the x, minus the integral of v du, 6 e to the x dx. That one we don't need to use integration by parts for. That one we can just integrate straight up. So we end up with x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x, because that's what the integral of 6 e to the x is, plus our constant. Good or no? Any questions or issues with that? Did I go through that too quickly, or are we good? Okay. Now, you probably notice a pattern going on here. At least I hope that you notice a pattern going on here, right? Our first term there was x cubed e to the x, which was just exactly what we started with. Yeah, yes, Nick. All I did was integrate by parts. Let's see, once, twice, 3 times, right? So our first term was our x cubed e to the x. And then our next term was a minus, but it was just the derivative of x cubed, right? 3x squared. And then it was the integral of the e to the x. And then we had a plus, and it was 6x e to the x, and it was a minus, and it was 6 e to the x. So each time we're looking at the original function, and then the integral, and then the derivative, and then another integral, and then a derivative, and another integral, and a derivative, and another integral. And this is a pattern that will repeat itself anytime you have 2 criteria met. One is that you have a function that can be differentiated down to equal 0. So if x cubed can be differentiated down to 0, or for example, x squared over here can be differentiated down towards 0 eventually. And if you can infinitely integrate this e to the x or the sine x, right, or whatever the other function is, like I can integrate e to the x over and over and over and over again, right? I can integrate sine x over and over and over and over again. Right? There's no stopping doing that. It can be continually integrated. And if you have both of those criteria met, then we can sort of skip some steps with integration by parts and do what's called tabular integration. So I'm going to real quickly run through what that is with you on this other one right here. So we've got both of those criteria met. X squared can be differentiated until it is 0. Everybody agree with that? I hope, right? X squared, or the derivative of x squared becomes 2x, then 2, then 0. Then what's the integral of sine of x? Right, integral of sine ought to be negative cosine. And what's the integral of negative cosine? Negative sine. And what's the integral of negative sine? Back to cosine. So if you can do this and take integrals all the way down until your other term becomes 0, you can very easily come up with the right answer. So we're going to combine the first term that we took the derivative of with the first integral that we got. So x squared is going to go with the negative cosine x. Then the 2x is going to go with this negative sine x. And then this 2 is going to go with this cosine x. And we will have a plus between these ones, or a positive term there, unless there's a negative within it that makes it negative. Then the second one will become negative. And then the next one will become positive, and you'll just alternate back and forth between those signs every time. So the integral of x squared sine x, using integration by parts and the specific little trick of tabular integration, should become x squared times negative cosine x, so negative x squared cosine x, and then multiply the 2x by the negative sine x, and then take the opposite of it because we have a negative because it's the second term. So that becomes plus 2x sine x. And then this one should be a positive, and since both terms are positive, it stays positive, plus 2 cosine x plus a c. And that's tabular integration. We're going to do a couple more of those if that didn't fully make sense. But basically, the idea is take derivatives of the one function until you get down to 0, and then integrate the other function an equal number of times to match up with the 0. And then you just put them together, positive, negative, positive. So real quick, I want you guys to take a look at this next one while I answer a phone call from my mechanic, and see if you can figure out how to at least do the derivatives and the integrals of each of those two terms going down. I'll be back in a sec. Luckily, that was quick. Okay, so any questions on that tabular integration or no? Everybody good with that? You guys can all still hear me, right?
Yes.
No, Delphine, you don't have to state anything. Just if you can see in your head that you can do it, then go for it and do it. So that's going to make this one nice and easy, I hope. What is the derivative of 2x cubed? Well, first off, does 2x cubed plus 3x squared minus 2x plus 1 eventually differentiate down to 0 if you take enough derivatives? The answer should be yes, right? First derivative should be 6x squared plus 6x minus 2. The next derivative should be 12x plus 6. The next derivative should be just 12 and then 0. Everybody agree with that? Okay. And then this is why I was saying it'd be really good if you can just do these simple U substitution integrals in your head, because otherwise you're going to have to write out the U substitution for each and every one of these. So what's the integral of e to 3x? Should be 1/3 e to the 3x. And then the next one ought to be, again, multiplied by another 1/3, so 1/9 e to the 3x. And then 1/27 e to the 3x. And then 1/81 e to the 3x. Everybody good there? So we will then combine the original u with our first integral and have a plus between them. Then the next two with a minus, then the next two with a plus, then the last two with a minus. Good or no? So we should have 2x cubed plus 3x squared minus 2x plus 1 over 3 e to the 3x. And we should have a minus, and then that should become 6x squared plus 6x minus 2 over 9 e to the 3x. And then we should have a plus 12x plus 6 over 27 e to the 3x, and then a minus 12 over 81 e to the 3x, and I think we could simplify that down, right? That should become minus 4 over 27 e to the 3x, and then don't forget your constant. Good or no? Any questions or issues with that? Yeah, you can do it with a definite integral. Sure. And you just got to plug in the value at the end, whatever two values you got. All right. So got one more of these. Why don't you guys do this one on your own real quick, and we'll come back and check on you and see how that's going. So take, I don't know, take 2 or 3 minutes and see if you can do that on your own. Ready to go.